Going, please.
All right, welcome everyone to this February edition of our Oberlin Acoustics First Fridays online seminar. And this month we have Claudia, but it's not just her. She's has a whole big team behind her on this Bilbao project they have been working on for many, many years. So I'm going to turn it over to Claudia and she will explain everything. All right, Claudia?
Yes, I'm trying to record as well, but it seems that I can't.
Oh, you can't?
Oh, no, it is.
All right.
See.
Oh, no,
Okay.
there we go. I'm going to mute myself, Claudia. So.
There is echo again. Okay. Okay. Good morning, good afternoon, good evening, everybody. So we are going with Victor and maybe George if he wants to interrupt, and Unai as well. Feel free to interrupt when needed about the Bilbao project. Yes, it's a big collaborative work. I've tried to put the names of the people who've been involved, and I hope I haven't forgotten anyone. But there is a lot of people working on this and who are helping at different stages of the project. So I suppose that most of you know by now about the Bilbao project. I cannot change my slide. Okay, let me change the settings because I can't see the full slide. Okay, so this the Bilbao project is a large and unique data set, which is constituted of a set of violins with very carefully controlled construction parameters that we know very well, acoustical properties that have been measured on these instruments, and perceptual qualities that have been collected through playing and listening tests. So first, let's talk about, if I can, the construction parameters. And so 6 violins were built. It was a very controlled set of violins where everything was controlled, from the choice of wood to the choice of fingerboard and bridges and so on. And 6 violins with everything as similar as possible, except a controlled change in thickness, either for the top or for the back plate, were manufactured or built. So basically, each violin has either a medium, has one medium plate, and the other plate can be medium, thin, or thick. So on this line, we have the medium tops with a thin back, a medium back, and a thick back. And here we have the medium back with a thick top, a medium top, or a thin top. And to actually make sure that what we want to control, like everything except for the thickness, is well controlled, we decided to build the middle one twice. So then the differences between these two should be much smaller than the differences between any other two. So that's to control that we have achieved our goal. We carefully chose the wood, or I should say they carefully chose the wood because I was not involved in this part. So Unai and Roberto and George and the Billy team. And there were pieces of the same piece of trunk here for the tops, pieces of very similar wood for the backs. Then using a CT scan made by Samuel Sigmuntovich on Huberman Strad violin. So from the Strad, from the scan, then STL file was derived. And I don't think it's the object, is a topic here to discuss about all this step, because that was a very tedious step and a very difficult one. But I'm not going to talk about this today because we have already a lot to talk about with Victor. So this we have already covered on previous. Sorry, it's very annoying to have this echo coming, jumping, and then it gets a bit disturbing. So we have covered this in previous talks, and if you want to talk about it, we can always talk about it at the end of the talk. Then the plates were CNC rotated. Yeah, because maybe I should have started with the beginning, is like, because we wanted to control this instrument as much as possible, we decided to minimize the intervention by hand. So the idea was to have control by CNC rotors from the outside. So the outside of the plates were supposed to be left untouched. And then only the plates would be graduated from the inside. So after 2 years, we, and a lot of white nights, as we call it in French, like sleepless nights, especially for an eye, we got the plates, 6 plates and 6 tops and 6 backs, which were then graduated very carefully by Unai, Roberto, George, and the belly team. Then the boxes were closed and assembled. Then a careful selection of fingerboards, scrolls, bridges to end up with the 6 violins after a long time. Actually, on this picture, you can see more than 6 violins. And that's because to have a bit more variety, we thought it would be interesting to compare these violins with violins that would be made along the same model, but with slightly more relaxed constraints. So we had 6 what we call external makers who took part in the project and offered to make a violin. So they gave us the wood, so they had a bit more freedom. We gave them the density and they chose the wood. So it was not from the same tree. Their wood was CNC rotated, so we gave them the plates. Then they graduated the way they thought was good with this model. And then we gave them a fingerboard and we rotated the scroll for them. We gave them the bridge and the strings and everything. So we end up with 12 violins. And then to see as well what is the difference between the Huberman violin and another violin which would be built by one of the external makers, Roberto. We added a 13th one, which is was built by Roberto on a Plowden model. So we wanted to see whether it would be a complete outlier, because based on the Guarnerius model, or if it would actually share some properties with Huberman made by Roberto, because it's the same maker. So that's 13 violins. So the point, one of the goals of the project is to link the construction parameters with the perceptual qualities. So we have done a series of tests. So the first test which was conducted was a free categorization playing experiment. So basically, players were invited to play these 13 violins with blindfolded, and they had to make groups by similarity. So similarity was left open deliberately, and so it was up to them to decide what means similar, but what are the similarities between the different violins and which group they wanted to make. So they were free to make as many groups as they wanted, and at the end they had to describe each group and why they put this violin in that group, which were the shared qualities for each group. 25 players took part in the experiment. So how do we analyze the data of such a perceptual experiment? It's by means of what we call a hierarchical tree. And it's a tree because the distance between 2 instruments is represented by the length of the branch. So for example, the distance between the violin 9, which is a thin top, and violin 11, which is medium, is all this length. Okay. So what you can see here is we have some groups of instruments which were more put together by people. So these are the results for a subset of 7 players, because when we look at the data for the 25 players, we didn't see anything. People really made different groups and it was a mess. And so we decided to look whether we could find people, participants with different strategies. And so we found 2 subsets of players. One consisted of 7 players, and we have this 3, and another one that I will show in a minute. What is quite interesting with this subset of players is that they seem to be sensitive to the thickness of the plates, because they put the thin either top or backs together. The thick back and top are relatively close to each other. The 2 mediums were close to each other, very close, with another medium. The Plaudern, which was made by Roberto, is quite close to the Huberman made by him, definitely closer than many other Huberman. And then here we have some other instruments where was a medium, except for this one. So the belly violins, they are in colors. The other ones, so for the belly violins, we know exactly whether the plate was thin or was thick. For the other instrument, we had a look at their properties, and we could basically classify them, order them roughly between thin, a bit less than thin, a bit less than medium, then medium, medium plus, thick, too thick, and completely thick. And so that's what you see here, medium plus, medium minus, medium minus. That's the classification that we have done. So we have some grouping by construction parameters, it seems. But then when we look at the other subset of players, so that's only 5 players, but still we could identify this group of participants, we can see that here it's completely different. And we don't see anything related to the thickness of the plates anymore. And whereas the medium V5 is far away from the medium V11, while they were supposed to be the same, and this group of people put them together. So that's it was quite surprising, and we don't have no idea why. So when we obtained these first 3, we are very happy saying, oh, it seems that there is some correlation. But then when we look at these 3, we were like, oh, geez, what's going on? So we were hoping that by looking at the verbal data, so all the description that they gave for the different groups, that we could understand why they made so different grouping, so why they had different strategies. But unfortunately, we were not able to find anything in the verbal data as well, for many reasons. The first reason is that they were actually quite not so talkative, so they didn't say so much first, and then we could see obviously a lot of disagreement and variability. So we can't go much further than this with this set of data. They had to choose as well their preferred violin after the categorization task. And so here is a number of times each violin was chosen as a favorite for the 26 players. So there are definitely some instruments, especially the Bilbao set, and among them the one which were made deliberately, not working so well with a thick top or thin top or thick back. So they were never chosen. And we have the violin by Roberto, which has been chosen the most, 9 times. And then we have the thin back, and that came a bit as a surprise, because we would have thought that if any of the violins would be preferred, would be more the medium 11 or medium 5. But the thick back was really liked. And then equally liked to the one by George, I think. So, but we can see as well that 1, 2, 3, 4, 5, 6, 7, 8 violins out of the 13 got chosen at least once. So you can see as well the variability of preferences, which we have already seen in all the perceptual tests that we have done in the past. Then the listening test. So we did a listening test in the auditorium in Bilbao, and we had 65 participants. We were mainly bowed string players, but we had some other musicians as well, like pianists, and we had a bunch of violin makers, mostly from ballet school. The violins were compared in different ways. So they were under the format of what we call triads. So it was 3 violins, and they were played violin A, violin B, violin C, and then start again violin A, violin B, violin C. And people had to select the 2 which were the most similar and the 2 which were the most dissimilar among the triad. We had pairwise comparisons under the format AB, AB. And then we had an individual evaluation of the 13 violins. So the 13 violins were played in random order by 1 player. And then they were played again in another random order by another player. And they were playing 3 excerpts, 1 on the low register, 1 on the mid register, 1 on the high register, after a free playing of about a minute on the violin, just to, so they were basically given the violin, they were able to noodle on the violin, you know, explore different things in different registers and different dynamics. And then they were playing the 3 excerpts. The 3 excerpts were different for the 2 players. So the comparisons by triad, we had the 2 medium, and then the thin back. And we wanted to check whether the 2 medium would be considered as closer than the other one. And here are the results. So the 2 violins that are most similar were considered to be 5 and 13 by 23 listeners, 11 and 13 by 13 listeners, and 29 found that it was 11 and 5. So we can see that it's quite equally divided between 11 and 5 and 5 and 13, which came a bit as a surprise. But at the same time, it's, as I told you, the 2 subsets who took part in the playing test, some people put 5 and 11 very close together, and the other subset, they put 5 and 13 very close together. So we can see the same strategies among the listeners here than we had for the players. Why, we still don't know, but we observe this. For the most dissimilar, again, we had the most was 11 and 13, and that's because the 2 subsets are different. So, so it's similar, and we had 11 and thin back for the others. And then here the 20 is 5 and 13, like subset 1. So we can see that in the listening experiment, we had similar results to the playing experiment. So we thought, okay, there is something here. We don't understand why some people find the medium and the thin back closer than the 2 mediums. But at least if people doing the listening test and people playing the instruments agree, then there is something to investigate and understand. We did another triad, which was the 2 thick plates. So one is a thick back, one is a thick top, and one of the medium. But here the distribution of the votes was not significantly different from equipartition. And so we didn't get any results from this. The pairwise comparisons, we asked different questions. Which one has a better tone quality, the timbre, in the low or in the high register? That was 2 questions. Which one is more powerful overall, and which one has a larger dynamic range? And so they had this usual scale to answer for each question, where, you know, if you put your your mark at the middle, that means that A and B are equivalent for the things that you are judging, so the tone quality or the power. And if you go on one side is violin A, which is superior, and if you go on the other side, it's violin B, which is superior. And here are the results. So we have 4 questions: the timbre in the low register, the timbre in the high register, the power, and the dynamics. And here we have different pairs that were compared. Here we compare the thin top and the thick top. And we can see that the thin top was favored over the thick top for all 4 criteria. Here we have the thin back compared to the thick back, and again, the thin back was favored for all criteria. Here we have thick top and thick back, and we can see that the thick back was favored for all criteria. Here we have thin top and thin back, and then here we have the thin top, which was favored for the timbre low register, and otherwise there was a equal. And the 2 medium, we can see that they are rather equal, except a slight preference for the dynamics of this medium violin. So what do we get from this? We can see that thin is better than thick, because the thin top was favored of the thick top and the thin back was favored of the thick back. If thick, it's better the back than the top. We can see that the thick back was definitely favored over the thick top. For the thin top, for this particular comparison, we have a contradiction with other evaluations, because as I told you, the thin back, for example, was really favored by the players. They found it, there was their second favorite, and we have other evaluations where it's really favored. So we are a bit surprised to see that they were, when compared by pairs, there were so little differences between the 2 violins, and even a preference for the thin top for the low register. So this is surprising. And then here, yeah, this is what we could have expected. We designed built the instruments so they were similar, and we were pleased to see that they are mainly very similar. Though not identical, and we will go back, talk about this more later. And then there is this last part of the listening test was the evaluation of each violin independently, and that's really the part on which Victor did a lot of work. So the floor is yours now.
My turn.
Yes.
Okay. Hi, everyone. So I worked on the data from the listening part, in particular on the verbal data. So 49 listeners wrote comments, and the most part of these comments were in Spanish. Some of them were in English, and I think one was in French. And that all those comments made a database of 2,680 verbal units, which were translated to English thanks to the help of a Spanish violinist who happens to know the language of the violin or the violinistic terms, then the European violin makers that took part on the project, and Claudia, to ensure the relevance of this translation, because there is no a dictionary of violinistic terms. Okay, so what we did with all these comments was to classify them, and we looked the previous work of classification by semantic categories, and we had all these comments classified in 19 key features, which are in the right part of this table. And all these key features, like the brightness or the power, were themselves categorized in subcategories, perceptual subcategories, which were also classified into main perceptual categories. So we have 5 main perceptual categories that are the timbre, the intensity, playability, interest, and balance, being the 3 most relevant categories. I think they were like the 80% of all the comments: timbre, intensity, and playability. So what do we do with Well, here is an example of this classification of this, what we have called microconcepts, into the key features. For example, if for a given violin, one of the listeners said that it had a very bright E string, this comment will be classified into the brightness key feature. And the other example, for example, for sweetness, if they said that it has a very sweet D string, this comment will be categorized as a positive microconcept into the sweetness key feature.
But the difficulty here is like it's giving you examples where sweet, of course, it goes to the sweetness category. A lot of work and many hours of discussion with many people, many makers in the Bilbao team was to, what do we do with words like, you know, sharp, shrill, metallic? Do we put it in sweetness? Do we put it like metallic could be as well in the brightness as a negative concept? So a lot of discussion was already done on this to end up with a categorization that can probably be discussed and argued, and it would be fine if other people would propose something else. But we thought that among us with different languages and coming from different backgrounds, it made sense. Because of course, everything depends on this categorization afterwards. So remember that what we obtain is based on that categorization, and which can be argued, but we thought that by many discussion, it made sense.
That's it. And so finally, we will have for every key feature a number of comments which have been labeled as positive or negative. And all the comments that were not classifiable in those terms were rejected. So for example, for a given violin and a given perceptual category, for example, for brightness, let's say we have a certain number of positive comments and a certain number of negative comments. So we defined the valorization as the difference between this number of positive comments minus the negative comments, and all this normalized by the total number of the comments that this violin has in this data set.
For all categories.
That's it. So this valorization gives us a quantifiable perceptual unit, we will say. But we are going to look not this valorization, but the deviation from the mean of all the violins to avoid bias. So, for example, for the category of power, we will have, let's say that the average valorization is +3. It's like everyone thought that the violins were more or less powerful. To make the difference between one violin or another violin, we will see the deviation from this average. So if one violin has +6, it will be higher than the average. And if another violin has +1, it will be perceived as powerful, but is less powerful than the other violins.
So the idea here is like when you ask a lot of people to comment, basically every violin will be commented as being bright at some point. Every violin will be commented as being nasal and powerful. And so the idea is to see, are some violins more powerful than others? So that's one reason. The other reason is like when you have to comment a violin during a listening test, you will only mention what is most striking. So even if you don't say that this violin is bright, maybe it's still a bit bright, but it was more important to mention that this violin was powerful and rich. And so it's interesting as well to see, these deviations compared to the number of comments. And that's why we divide by the total number of comments for that violin, and not just the total number of comments in that category, because we want to see what is the percentage of, because this violin is bright, something very important because everybody mentioned it. But then everybody mentioned it was powerful, and everybody mentioned that it was this. And in the end, it's not that interesting. Or is it really bright to the point that mainly the only comment that people made on that violin? So this is really to try to grab what really mattered for people, because usually, for example, like not nasal, if you don't think that the violin is nasal, you will never say it's not nasal.
And we found no comment of like negative in the category of nasal, because there were no comments that said not nasal. All the comments of this category were nasal. So
that's why you need to compensate for this type of bias.
So for example, if you don't have any comment about nasality, if all the comments of nasality are negative, that means that this violin is positive in that way, that not being nasal. Okay, so what do we do with all these deviations? We can represent them in these diagrams that here I show you. These are the Vele violins, and the deviations are colored as with green if they are positive. Positive means that this violin is higher than the average on this particular category. For example, in timbre, violin 13 is well above the average. And on the other hand, we will color it as with red. In the contrary case, that's it. That is when the deviation is negative. So this representation allows us to quickly and very easily see how these violins have been perceived by the listeners of the test. This representation gives a similar picture as the pairwise comparisons. We can see that, for example, for the medium violins, they are both more or less on the average, except for violin 5, which is positively perceived in terms of playability, just in the same case as the pairwise comparisons.
Because playability includes dynamics. And we saw that during the pairwise comparisons, this violin was slightly favored over violin 11 for dynamics. So it's consistent.
That's it. Violin 13, which was the second most favorite violin for the players, it was pretty well perceived. Well, it was better perceived than others. And if we compare think back versus think top, it is better think back apparently from this data set. And for these two violins, thick back and thick top, they were not very well perceived, let's say. And all this is in agreement with the previous listening tests.
Except for the thin back, which is favored over thin top. But which is in agreement with the players' point of experience. So.
And as we have categorized all these comments in at different levels, we categorized them first as key features. Then these key features were grouped into the subcategories, and then these subcategories into the main perceptual categories. Given that, we can go further and have more detailed representations of their perceptual categories. And this gives a lot more information about how these violins were perceived than the star rating system that was part of the listening tests. The listeners were asked to rate from 0 to 5 stars the violins, and here next to the name of the violin or the number of the violin, we show you the average note of this star rating system.
We can see that's not big differences between the violins. While when you look at the colors, you can see big differences with violins which were really less liked and violins which were really favorite. And so the verbal data here really bring more information about how the violins were perceived than just the rating system. So
this well, first, we would like to see if the listening and playing qualities as perceived by the listeners of the listening test and the players of the playing test were similar. So in this diagram, I show you the groupings that were made by all the players. That is the average grouping of all these violins.
So this is a hierarchical tree as well, slightly different from the one we presented previously, which was more like a radial tree. But we decided to choose for the rest of the talk to use this representation because we think it's less misleading. But it's the same principle where you can see grouping. So here we can see basically the tree divided in two main groups, and then each group is divided in two groups. And the smaller the lines are, the closer the two instruments were put together. So here we can see that 5 and 13 were put a lot together, and then they were put with 6. And you see, so it's the same type of representation, just slightly.
That's it. In this case, the distance between the violins is not strictly following this the line, but just the height of these lines. And so we wanted to see if there were a correlation that is the links between the playing test and the listening test. So here we chose to represent all the violins of the groupings made by the players and the perceptual categories as perceived by the listeners. And if we compute the distances also between the violins from this data, from the perceptual characterization of the violins from the listening data, we will be able to compare both groupings. So we can do the same hierarchical tree, which is in this case called dendrogram, for the listening test, and then find if there are similarities between both groupings.
Because just to complete, you know what, this was a dendrogram that we already showed you before, the hierarchical tree from the playing test, and then we decided to put underneath the perceptual valorization that Victor has just explained. But to actually compare valorization like this with dendrogram is more like, you know, visually. We could see, okay, we can see that 1 and 4 were put together by players and they were perceptually similar for listeners. We can see here 13 and 6, you know, seems perceptually similar for listeners and they were put together by players. But this is a very a qualitative way of comparing the two types of data. So the idea here is to transform this valorization into distances between violins, like we have distances which were made by the players. We will compute distances for the listening test, and then we have two sets of distances. One set of distances for the playing test, one set of distances for the listening test. And then, because we have distances, we can do some correlations between the two types of distances. So it's a quantitative way of checking how the perceptual, quantifying the perceptual evaluation during the playing test with the perceptual evaluation during the listening test.
And these distances will build this dendrogram. So here, what we see is the groupings of the violins that have the most similar diagram. Let me take an example. For example, violins 11, 9, and 3 are, if you see the diagrams, they are violins that are perceptually very close in terms of this distance that Claudia has just explained. But unfortunately, is not the case in the upper diagram. So for these 3 violins, whereas for the listeners, they are pretty close in terms of these perceptual categories. I remember timbre, playability, and intensity. It happens to not be the case for the players that played these violins. Another example, for example, these violins 2, 6, and 13, which were pretty well.
If you're zoning out, I can explain it to you later if you like.
they will pretty positively perceived by the listeners. They are close in for the listeners, but that's not the case. At least for violins 13 and 6, yes, but not for violin 2. And the last case, which is which we find that they are together in both the listening tests and the playing tests, are the violins which happen to have a thick top or a thick back. They are violins 1 and 4. They were perceived similarly by the players and by the listeners. And the correlation, it's a unit that says us, that tells us if both dendrograms are similar or not. If this correlation is close to 1, or at least higher than 0.6, more or less, or 0.7, this means that both dendrograms, both hierarchical trees, are compatible. There are links between these distances. And unfortunately, it's not the case for these two. That means
we can see here it's 0.17, so it's very low. And it was explained why, because we see we have groups which are not the same for both types of participants.
That's
so, it. Yeah,
we see here two big groups, and here we see a bigger group and then a smaller group. So this tells us that both distances are not related. So as we can go further in the perceptual categorization, we wanted to see if we could find a better correlation. If instead of seeing the distances from the 3 main categories, we see the distances from all the key features, because we had the data set and we had all the values, but the correlations were pretty much the same. It did not improve. So we had the same conclusion.
So the takeaway here is that there doesn't seem to be any link between the perception from the players and the perception from the listeners. So now we are going to talk about the acoustical properties that have been measured, or at least some acoustical properties that have been measured on these violins. We had 3 types of data that were measured and recorded. We have recordings made by Unai on the 25 or 26 players who played during the playing test, during the categorization task. At the end, Unai asked each of them to play a small a scale on each violin. We have radiation measurements, which were taken on the finished instruments before they took part in the playing and listening test. And we have vibroacoustical measurements, which have been made at different stages during the construction. So after CNC, at different types during the graduation of the plates. But this, we haven't analyzed them yet, and so we are not going to talk about them tonight.
So the recordings that we have, that Unai made, are recordings of all the violinists that took part in the playing test. And it is a chromatic scale, a G chromatic scale of 3 octaves. So it's on all strings until the uppermost, not uppermost, but the G on the E string. So 23 players were finally considered, because I don't know if we didn't have at the beginning, there were 26, but there were 3 of them that were missing. And we will compute the long-term average spectrum to have one representation of the acoustical data from these recordings per violin. So the scale that was recorded from this scale, we can compute what is called the long-term average spectrum. It is basically the average power for every frequency over all the duration of the recording. This gives us like a kind of frequency response of the violin, and here I chose to represent one of the violins, the violin 5. The long-term average spectrum of this violin, but averaged by band. And the band that we are considering here are thirds of octave. Okay, so it's a bit complex, I know it, but in this representation, this particular representation, we chose to normalize all the long-term average spectrum averaged by band on the first band considered band, which happens to cover the open G string. And I don't know if maybe also it stops just at the lower A, because lower A is 221 Hertz. So that's it. And here in this graph, I show you all the long-term average spectrums averaged by thirds of octave from 16 players. Why those 16 players? Because they were the players that played the same scale. Because unfortunately, not all players played the same scale. Some of them didn't play it chromatically. They did an A major string. Others did not do the full range and did only 2 octaves. So in this plot, there are those that play exactly the same scale. And to give you another.
Well, first, before okay. Maybe, so what is really striking here is that you have huge differences between players. Okay, so for example, for this band, you can go between 30 to 50. So there is 20 dB difference for different players. And so that's really, it was a bit shocking for us that could be so different. And because we normalized by the first band, it's not because one, for example, player consistently played at a lower level, you know, so one could have played mezzo piano and the other way 140. No, because by normalizing by the first band, that should take into account the overall level. So these are really levels because some players were able to emphasize more some of the harmonics in this range and some more at the top, and so some are violins you can see are rather at the top in most cases, but for some others it can be here this one is at the top and then it will be at the bottom later, and so we don't know how they manage to change the output of the violin by so much. You know, that there are slight differences, fair enough, you know, they play closer to the bridge, they apply more force, but to that extent, to have 30, sometimes between 20 and 50, 30 decibel differences, and that's really huge. So we want to compare this to, for different violins to see whether some violins, or if it was just the case of this violin, and then we realize that for another violin, like violin 11, we have
the same case.
Yeah, quite a lot of differences in different bands for the different players.
That's it. And given that both violins have both medium construction parameters, so thick plate thickness. And as an example, we can show also that for violin 4, it's exactly the same than for the others.
And that's the thick top violin 4. And you see the difference between different players is very similar to the differences that we have for other violins. So we have consistently 20 to 30 dB difference or some for a given band.
So we thought that, well, we have to avoid this difference between all the players, we should average all these bands over all the players to finally see, but because what we are interested is not, well, we are interested in the way the players play, but here we want to see the difference between the violins. So if we average all these frequency over the players, we should see if one violin or other violin is more similar or more different So here in this plot, I show the average over all the players for 3 given violins. The violin 4, which has a thick top plate and a medium back, and violins 5 and 11 that were the violins that were that were built in the same way with medium top and medium back. So this average over all the players gives us one long-term average spectrum per instrument.
And what we can see here is that differences between the instruments, the maximum we have is here, is not even 10 dB. So the differences between the instruments in average, it's much less than the differences you can find between 2 players on the same instrument. So what is the identity of a violin? It's a good question.
Yeah, in particular in this plot, we did not normalize on the first band, just to see because we average over all the players.
And we really wanted to see the absolute differences between the instruments, in particular if one instrument is quieter than the other. But at the same time, we see that people could play very differently and emphasize different bands. But at the same time, we could see as well that there was some consistency in what players and listeners say. For example, violin 4 was really disliked compared to 5 and 11. So there must be something that people are sensitive to, which is universal to some extent. Even if they can play with, when they play, they highlight different bands. But it's not very clear. That's something we'll get back to in the conclusion.
So we wanted to see if the distances between these violins from the playing test data, that is from the hierarchical clustering that they made from the free categorization task, was related by with the data that we collected from the recordings. That is from the long-term average spectrum that we have just shown. So based on previous work on a study on loudspeakers, we decided to use an auditory model that takes into account the physiological constraints of our auditory system because finally our ears are not perfect, they are not perfect microphones, so some frequencies will be perceived better than others, and we chose to use this model to have a perceptually meaningful frequency response from the recordings, so from this long-term average spectrum. So here in the left, there is this long-term average spectrum that has been averaged over players, so for a given violin. And when we filter it by this loudness model, we obtain this overall specific loudness, which is like a perceptually meaningful frequency response.
So that was for the recordings. Now we'll quickly go through the radiation measurements. So these are, I suppose, many of you, at least people from the Oberlin workshop, are familiar with these measurements. So how do they work? You measure the radiation via a microphone. The violin is excited with a little hammer that you can tap on the bridge either horizontally here on this corner or vertically here. So two types of excitation. You turn the microphone around the instrument, or you turn the instrument around the microphone, doesn't really matter which way you do it. And so the usual number is like 12 angles. So we have two types of excitation, 12 angles, and that's 24 measurements per instrument. And then these 24 measurements are usually averaged to get only one radiated frequency response function per instrument, because looking at 24 measurements is very difficult for our eyes and brain. And so usually we like to average, a bit like what we did before. We like to average to get a picture. So the frequency response function here is an example for a given violin. So the classic way, which was described by Joseph, is to take the RMS average over these 24 measurements. But there could be other averages to choose from. And we could as well do some post-processing after we have averaged these measurements, in particular via the loudness model that Victor has just talked about that we use for the recordings. Or we could do some band averaging that is classically done at Oberlin to see a bit better, because when we have a very red like this curve, it's not so easy. So we like either to smooth it or to band average. So there are different possible treatment processing that we could do to these measurements. And we thought that having this unique data set, we could maybe choose or like explore if there are some averaging or post-processing which are more perceptually relevant. So the idea would be to, using all this data, to actually try different averaging and different post-processing, and then try to correlate this with perceptual properties and see whether one type of averaging and one type of processing gives better result, better correlate with the perception. For the averaging method, for example, we can take into account the fact there is a bowing angle. So when you say, well, we average over vertical and horizontal, that means that we consider that both are equally important for the violin. But we know that you never play at exactly 45 degrees. You play rather at 30 degrees for the low and high string, and like rather flat for the middle strings. So we can write that the transfer function could be as a function of theta. So it could be cot theta times the measurement which was obtained by an horizontal excitation plus sin theta times the measurement which was done vertically. So that gives us 12 functions per violin. We have 12 of each for 12 theta. And then we can try to average this either with an arithmetic mean. We just do the complex average of the 12 functions here. Or we could do an RMS average, and it's represented here as a function of theta. So here are results, which show we only present the result for one angle, which is a 45 degrees angle. And we can see in red, it's the complex average. In grid, it's the RMS average at 45 degrees. And then in blue is the RMS average of 24, of just the 24 measurements. After that, we said that we could try different post-processing. So one is band averaging. So here we chose what we call the Bailey bands. So basically by looking at the different measurements of the different violins, we identified bands where we thought that, oh, in these bands, we have like clear, distinct features, and we can see that the violins differ during this band. So it's bands that were specially designed for basically the Huberman model. And so here we have the RMS measurement with the 24 measurements in light gray. Then we are smoothing by semitone, and we have two different averaging as well, the third octave band in red or the blue for the belly bands. So basically then what we will do is we will, and after that we can still apply as well a loudness model to get an overall specific loudness over this radiation measurement. So now that we have all this data, both from recordings and radiation, the idea is like, can we do some correlation between these? Because it's always been a question like, okay, recording is what is the closest to what we should hear because it's when a violin is played by a player. But at the same time, it's difficult to deal with because that means you need a player, and then we have seen that different players will play the instrument differently. So how many players you need to have like an average picture of the instrument? And so the radiation measurement, which this is the reason why it has been so used, is like a way to get one measurement without anybody to play with the instrument. But of course, it always raises a question, how informative is the radiation measurement compared to a violin which is actually played? And so we really wanted to explore this link between measurements made without player and recordings made with a player. And so for this, we will calculate distances between the violins, like what Victor explained earlier, where we calculated distances between perceptual properties. Here we will calculate distances between acoustical features.
That's it. And we can do it from the recordings and from the radiation measurements. So basically, the distance, we can choose an arithmetic. We can find the distances of along all the frequency axes of both frequency responses. For example, for a violin A and a violin B, it will have different frequency responses. And then we can compute, we can calculate all the difference, as I will show you right here. For example, this is two specific loudnesses for two given violins. And we see that they are pretty different here. So we will sum up all this difference and then average this difference to finally see if these violins are more similar or less similar. If this distance is pretty close to 0, for example, that would mean that these violins are similar in this way. This is for recordings, and for example, for the radiation measurements, if we take the example of the belly bands averaging, we could simply calculate the difference of both violins for each band and then average them to see if this distance is close to 0 or not. And this distance, this set of distances between all the violins will give us a dissimilarity matrix that will construct, will by this dendrogram that we previously showed you, which is a representation of a hierarchical tree. And what we can do with all these dissimilarity matrix, we can find correlation between these matrices. That is, if we find that two dendrograms have the same groupings, the correlation will be close to 1. And in the other case, if these groupings are pretty different, this correlation will be near 0.
So it's really a very similar method that we have been using since the beginning. So it's calculating distances between violins and see how these distances correlate for different types of distances. But it's always a distance, but it could be distance between two radiation measurements. It could be distance between two recordings. It could be distances between two perceptual evaluations. And so the idea then we can, because we have distances for different types of measurements, we can then correlate these distances. So are the listening distances, how do they compare with the playing distances? How do they compare with the radiation distances? How do they compare with the recording distances? So it's always the same principle is, look, you apply some processing, you calculate distances between the violins, and then you correlate these distances. So here, for example, we have the recordings, the distances between the recordings, and the distances between the radiation filtered by the loudness model for different types of averaging these radiation measurements. So we have here, when we do the complex measurements for different angles, here we have the usual RMS average of the 24 measurements. And here we measure the RMS, but for different angles as well. So you don't need to know exactly how everything was computed, but the thing to see is that the highest correlation was when we use the RMS 24. So the usual way. That's what correlates the most with the recordings. And so it could be a good justification of why this, the usual method that is widely used is a good candidate. But we can see that this is the highest correlation by far, but it's not very high. It's only 0.5. And that was a bit, it's a bit sad, disappointing, I would say, because that means that the correlation between something we can measure in an objective way, you know, without musician and just with a hammer, how close is it to what you can measure with players? Not that close. We tried as well, instead of filtering the radiation measured by the loudness model, we tried just to use the belly bands, to average by belly bands. And it's a bit increased. So it seems here that to correlate with recordings, it's better to just average by bands that has been carefully chosen rather than to actually filter through the loudness model. Here in this case, we get a slightly better result by taking into account an angle, but considering the simplicity and the ease of taking the 24 measurement, we think we should still keep using the 24 RMS averages for sake of simplicity, because we don't gain that much. Still, we could imagine trying different things. That's only one way, but we could think as well that maybe we shouldn't take the 24 measurement. Maybe we should take only some of the front measurements, because after all, when the player is playing and considering where the microphone was, maybe some from the back is not coming through a lot. So there's still more to investigate, but there is so much to investigate that at some point it's easy to lose track as well. So we've started by taking all the 24 measurements into account. Maybe we could try to reduce maybe some of the measurements and see whether it can be improved. For the recordings, we only use recordings filters through the loudness model because that's what is the closest to what we hear. Okay, so now that we have talked a lot about the acoustical properties, we would like to see how they correlate with the construction parameters. So another dendrogram, so this one is based on the distances between the violins in terms of radiation measurements. Here we took the 24 RMS average because we thought it was the best, and we averaged with the belly band. And so we computed the distances, and we obtained this dendrogram. And then it's interesting to see what are these violins and how they are grouped. So here we have 11 and 5, the two medium and medium. And surprisingly, in terms of closeness, in terms of like radiation measurement, 11 is closer to 1, which is a thick back, than it is closer to 5. And this is like, what? Especially we think that they are still very close. So why do we get such a close relationship between 11 and 1 in terms of radiation? That's a very big surprise. The medium top thin back is here. Here we have the thin top, and we have the thick top as an outsider. You know, it's not grouped with any other violin. And this is not so surprising because many people can recognize this violin and they already say it's quite different. But still, we are a bit surprised at why 1 is here and not with 4 or closer to 4. It's quite surprising. And why that 5 and 11 are close? Yes, they were built to be different, to be similar, but 1 was supposed to be built to be quite different, and it's actually very different in terms of the thickness of the back. So why does it get so close to 11 and 5? I don't know, something to discuss. So now that we have looked at this link between construction and acoustics, we can look as well at the links between acoustical properties and perceptual qualities. And so here we will not present the dendrograms anymore, but just look at the correlation between the distances. So we have the playing test on the left, and here we have recordings filtered by the loudest model. No correlation, very, very weak correlation. So we could not explain some of the result from the playing test by the way the players played. For example, we thought, oh, we identified 2 subsets of players. Maybe by looking at their recordings, we can understand why they grouped this instrument together and the other instrument together. But no, it doesn't make any sense. We looked as well at trying to understand the playing test from the radiation measurements. And again, the correlation is very low. So basically, the results from the playing test don't correlate with anything. But the good thing is that the results from the listening test correlate quite well with the radiation. And so that shows that justify some use of doing these 24 measurements, because that can still predict at least how the violins will be perceived by listeners. And that can be explained by the fact that the radiation measurement really takes into account the spectral properties of the instrument, because you only look at the spectrum. And the listeners, that's basically the thing that they are most sensitive to, because it's very hard for them to judge playability, for example. You know, they don't have the feedback of the player. They don't know what was put in as an input and what is the output. So what they really hear is the color of the instrument, the timbre of the instrument. And so it's not, it's quite reassuring to know that it's correlated to how the violin radiates spectrally. While for playing, there are plenty of other things which are taken into account that we don't measure, neither with recordings and nor with radiation. Players can be sensitive to, just for example, if one neck was slightly more rigorous, or then he could say, oh, I didn't like it, and then he would put it somewhere else, you know. Or he can be sensitive to how the sound is ringing at the end, and that's something that we don't measure. Or it can be sensitive to the transients, and this we don't really measure, or we don't look at it with the radiation measurement. And so, plus the task was very difficult as a player to listen, to play these certain violins was very difficult. So maybe that's why it's so difficult to make the links. So conclusions, I think I've gone through most of them just by summarizing what I've just said before. So from the listening test, there are quite clear perceptual differences, which result from construction differences, and that makers can learn to recognize. In terms of timbre, we can see that for this model of arching, so the Huberman model, we can see that it's better to be on the thin side than on the thick side. And having the correct thickness is more important for the top than for the back. And based on further experiments that we haven't presented here, we were able to see that the fault due to a wrong thickness cannot be compensated by adjustment. So we try to work on the Bilbao violins to improve the thick top and the thick back, for example, by changing the bridge or sound post, but it was not really possible. The perceptual properties based on the listening test correlate well with the radiation measurements, which were filtered by a loudness model. So we need to do this filtering probably when we look at the radiation measurement. But no correlation with the playing test. And so that was a bit disappointing because we did the categorization task thinking that it's supposed to be, the most natural, because that's something we are used to classify, put things together without, and it prevents us experimenters of putting any a priori, on the participants. But unfortunately, it does not lead to a strong conclusion in our case. And we think it's because there's a high individual variability and the difficulty of the task. Then there are many questions which remain. We saw that there are much larger differences between the players and between violins. So what is the identity of a violin? And can we really, how do we link this with what we have just said? Well, some instrument was still disliked compared to others. So how does this come from? While when you look at the recordings, you can have it's a big mess. And there is this odd case of violin 1, where in terms of measurement, it's very close to 5 and 11, but then it was really disliked by both players and listeners. That's the only one where really they agreed completely on this. So why? And so maybe because of playability issues that are not measured in the radiation, but maybe in the bridge admittance. So we really need to look at this data. But at the same time, listeners are less sensitive to playability than players. So it's maybe not the good reason. And then there could be this ringing issue, and then comes back to what Colin is fighting for. He always says that we should do the measurements not with the damped string, but with the strings undamped, so we can hear this ringing, because when you play an instrument, this ringing is important. But how to access information now that the radiation measurements were with damped strings? And from the recordings, we tried to listen to this, and we couldn't hear anything either, because it was legato scales. So you don't hear the end of the notes.
You can hear the ringing, but not really make clear difference between violins.
So that's it. I hope we haven't lost all of you, and that you are ready for some discussion.
Well, thank you very much, Claudia, and the whole team, you and I, at the Bilbao School. I mean, this is a huge project. I think it raises a lot more questions than it answers, of course. And so just a reminder, if you have questions, please use the raise hand function. It should be under your reactions at the bottom of your Zoom interface. And Jim, would you like to start with your question?
Just on your remark about larger differences between players than between violins, my immediate reaction to that plot is that what you were seeing was room acoustics. It's easy to get 20, 30 dBs difference by moving a little bit in a reverberant space. I don't think there was any control over exactly where the players were standing. Now, did you do the same player twice on the same violin? That's you need a null test here to see, is it really the player that's different, or is it that they were just moving around a little differently in the space and this is all room acoustics?
Well, Unai, I know that Unai put some marks on the ground where they had to stand, and the microphone stand didn't change. But then obviously some were shorter, some were taller, and maybe they were doing this. So
did you try an null test?
Sorry.
But I don't think he measured the same player twice. Unai did.
No, no. But
I
all of them play that
the average
in the same
over
right
all the
position.
violins per player, but I don't remember. Just to check if there were difference by player.
Yeah.
But I don't know where I have it.
But then that doesn't
Because
answer.
as I said, I computed the average of all the frequency responses over all the violins for each player to see if some players were normally, on average, more powerful than the others. But I have to look for that plot.
Yeah, I mean, that's easy to believe. I don't think a bowed string really allows you to control levels in individual bands in any kind of systematic way, whereas room acoustics easily allows you to do that. So that would be my first guess, is that this is all an artifact of room acoustics. Microphone measurements are a nightmare. Never do them.
Yes, just to amplify what Jim has said, I found it's very difficult to vary the output amplitude on a bowed string on a real violin by more than 20 dB. 30 dB is about the maximum. So, yeah. Let's go to Andrew Brown. You're muted.
There we go, 2 buttons instead of 1. Hi, this is a great study. Thank you for presenting. And I have to echo the sentiment about the room acoustics. My work on the double bass also pointed very strongly in that direction, that the player and the room acoustics might be far more significant than the effect of the flat back or the round back bass. And so that's a big bite to chew, and good luck on that. Yeah, perhaps one solution would be to have more than one microphone channel in the room among the audience, or a near field and a far field, and you could play with more than one input to try to mitigate that room acoustic factor.
But then if it's such a big factor, how is that like then a Brownian compensation? We know that this band is higher, and then how do we compensate for this, you know? If it makes such a big difference for different players, how do they can?
Well, I find it very interesting. But the player is a magnificent, artistic machine as such, and I think the player gets that room feedback, especially in the case of the double bass, where so much of the low frequency sound is coming back from echoes, that they adjust to it.
Yeah, but that means that because we could see that the player, when they were playing the different instruments, they were not necessarily always standing at the same position, you know? And so how do they know that the 20 dBs in that band is due to room acoustics or due to the fact that the violin is different?
I wouldn't argue about the 20 dB. That's out of my
I think you're asking the wrong question there. You have a bunch of measurements with no control. You see a big spread. You look at the factors that are available, and you say, which things do we know can create a big spread, and which things do we know cannot create a big spread? Room acoustics is well known to be able to, with a single microphone, is well known. You can get 50 dBs at a single frequency just by moving a little bit by where your microphone position is. Benaid was very hot on this. There's a certain amount about this in his book. Evans' talk from a little while back on the difficulties of microphone measurements but it's taking us off into a different world when none of us are probably experts in room acoustics. There are people around who are. It's a matter of controlling for it in the experimental method rather than agonizing about how does our brain do it. That is taking us off into different worlds. It's all this stuff about the precedence effect and early lateral reflections and all the things that, I mean, the next talk coming up is about concert halls, isn't it? Fan, I saw.
Yes, it is. David Griesinger is who happened to be with our group in our 2012 Paris experiment. He's going to give a talk on concert hall acoustics. So that should be very interesting. Just one little comment. If you want to learn about the effects of room acoustics on loudspeakers, the standard reference is Floyd Toole's book. Forgot the title of his book, but I mean, he spent pretty much his whole professional life investigating that subject. So look it up.
What did you say?
If you want to know the sort of the what is known about the effects of room acoustics on loudspeakers and the perception of sound coming from loudspeakers, the book to read is by Floyd Toole, and it's,
Fan, put me on the screen. Here's the copy of the book.
wait a minute. How I don't know how to put you on the screen.
Okay. The book is Sound Reproduction.
Yeah.
The Acoustics and Psychoacoustics of Loudspeakers and Rooms.
Okay. Everybody got that?
Okay.
Evan, you could type it into the chat. Okay. Why don't you do that? All right.
I definitely second the reference to Toole's book, especially because he used a model of loudspeaker analysis as part of the basis for your experimental design.
Mm-hmm. Okay. Okay. Are you done, Andrew? Okay, we're going to go to Anders.
Yeah, I wonder. It's still about this long time average spectra thing, and I guess was it a large hall you showed there, or medium large hall that these recordings were made?
It was in a rehearsal room.
11
Sorry,
five
room then.
yeah.
Unai, what did you want to say? The size?
Yes. The room was more or less 5-6 meters wide and 11 meters length.
It's like a large living room then, and I guess what Jim says is probably correct when you think about the room modes. But the larger the hall becomes, or the room becomes, the larger the model density becomes. And when you are at 200 hertz, the lowest note on the violin, the density is quite high in a room like that. So, and especially a concert hall. And what matters, I think, is how close you are to the microphone. And if the microphone is very close to the players, then you get more difference from smaller changes. If you are a meter from it or 1.5 meters, you don't get 20 decibels differences from the distance from the microphone. It's impossible. So I wonder, how long was the players from the microphone?
1.5, more or less.
1.5 meters. Okay, that's pretty standard. And in a recording, it's not just not possible. So this is variation from the players, I guess. And my second question.
So you say that it's not possible to get 30 dBs because of room acoustics?
No. And I work with room acoustics quite a lot. Not so much now, but I've been done so for 10 years. Lot of measurements. But I'm not an internationally known expert on it, but I'm pretty good at room acoustics actually. When it comes to the players, did they choose themselves how to play those scales, or did you tell them to play hard or loose or whatever? What did you tell them? Because a violinist will try to play nice, while if you play my long time average scales played on my bathroom laboratory here, it's terrible. It sounds terrible, but they work. I can repeat it.
No, I think, Unai, maybe you can answer this question, but the idea was to have a nice scale, mezzo forte, like middle range dynamics, so neither forte nor piano.
Okay. So
Yes,
they
I think
had
that
instructions.
I told them to play. as loud as they could.
Okay.
Are you said you said this? Are you sure?
Not, I'm not really sure, but not smoothly played. I think that we say to play quite well, not very strong, but maybe as.
Because there are definitely people who played rather piano. So
Okay.
I don't think you mentioned that it was as loud as possible. I think we agreed for a medium range dynamics.
Okay.
And also the
Yeah, okay, I'm
experience
happy.
of the experience of the players is not the same. So for some of them, maybe as the fortissimo doesn't mean the same, because I heard some of them did play with like a harsh attack at the beginning of each note, and other players played with a much smoother transient, still forte, but
Do you think players warm up using scales like that, or is it a part of their training repertoire, or is it not part of their regular training?
Well, I mean, the scale was used because with the scale you go through the full range, and it's like, you know, playing a glissando where you have, it's a frequency response, you know, to have
Yes,
the scale for this reason. And then after that, they had to record a little music piece.
yeah. Okay. Thank you very much.
Thanks for your comment.
Okay, John Fable.
Really appreciated it's great. I really appreciated the experimental design and the thoughtfulness of that. And I think we think of the brain as the other part of the instrument, right? As, you know, speaking as a scientist, I wonder. I'm always curious as to where has the results of this study lead you to want to study next?
there are so many paths, I think, in this project.
Yeah, there are still a lot of
Measures to
analyze, because we still have the bridge admittances that we would like to investigate, and have students who will start. So we have students who are looking at some transients from the recordings to see whether we could understand a bit. But we have only the microphone data, so the idea is to see whether we can get something from the microphone data. So it's just trying right now, and after that they are supposed to work on all the data accumulated at the different the vibroacoustic measurements accumulated different constructions. So still quite a lot of things to just with data sets.
Fabulous. I'll just mention the transients. It's intriguing because in some of my work with loudspeakers, the transient was one of the overlooked components in terms of perception of liveness. So that's very interesting. Yeah, I really look forward to following your work. Thank you.
Could I just make a comment here?
Yeah, go ahead, George.
Yeah, John was saying, well, where would we go? Where else would we go with this sort of thing? Well, I think, I mean, I'm talking to other makers, the two other areas where they'd like to have a variable parameter. The two most important ones are wood properties, particularly density, and arching design. But we still have the same problems of how to evaluate the perception. But one of the design considerations of this whole project was actually investigating how one could do such an experiment. Part of that was the finance. We had funding from Erasmus+. We had the cooperation of the ballet school, various institutions, and a team of people, and it's incredibly hard to organize. But I think it's a possible pathway forward to have these carefully designed and coordinated experiments because then we can set up situations where we can find meaningful answers to questions, potentially. Okay.
All right. Any other questions, John? You done?
No, that's it.
Okay, let's go to Colin.
I'm unmuted.
No, you're fine.
First, I'm fine. I have to thank everyone concerned with what is an amazingly large amount of work done by all the makers and Claudia and, well, everyone that's been involved in that project. It's obviously an amazingly major piece of work. And a lot of the questions I might have liked to have asked have already been answered, particularly by Jim. In terms of measurements in a room. And that refers to the recordings, and it refers to the measurements that are made in listening tests. And one of the interesting things that one can do is actually with a microphone, you can actually listen to the sound very close to the instrument, which is what Joseph Curtin does, of course, in his measurements. And the measurements, if you make them within 10, 20 centimeters from the instrument itself, they're showing something that is very much dominated by the instrument itself. But as soon as you get further away from the instrument, you're actually picking up more and more, and the further away you go, the more and more sound that you actually pick up in any measurements, like radiation measurements and in distant listening tests, is the sound of the room. And you can show that by just recording the sound of a tap test on an instrument and just seeing to what extent, in fact, and the signal is contaminated by the resonances of the room. So it's very difficult to make correlations, I think, with the instrument itself, because there may be fairly major changes in the instrument's acoustic properties, but they do tend to get swamped by the background that you're going to get of lots of upper resonances, the room itself. And lots of other people have made that comment, so or the equivalent to that. But anyone doing tap tones, just put a microphone outside, away in a room, not in an air-cooled chamber. So air-cooled chambers aren't perfect, and you'll get a very contaminated signal. You're looking at what you're measuring is the acoustics of the violin plus room, and the room can dominate. So, but the other thing that I've been enjoying doing, because I took some measurements of the internal sound on the instruments at a workshop, and I've been following Claudia's excellent and her team's excellent presentation, and I've been trying to and looking at the sound inside the instrument, which is another way of looking how the plates radiate sound, and correlating with the comments that were made on the association of the particular violins. And to my mind, that there is quite a lot of correlation between what for example, the listening tests and the playing tests with the actual acoustic properties of the violin. And it would be interesting, in fact, to interact with the group, just to follow up. It's very difficult to make an analysis as you go along because there's so much information coming along. But certainly the relationship between violins 5 and 11, which are the ones that have the medium, I think, and with 4, certainly show up when I look at the spectrum that you see on the inside of the instrument. So and the spectrum inside the instrument is one that is not contaminated in any way by the room acoustic. So that's just a comment. Thank you.
All right. Thank you, Colin. Joseph, want to go next?
All right.
Joseph Curtin. Sorry, we have two Josephs.
Oh, okay.
Joseph, I think you're muted.
He's not muted, but we can't hear him.
Yeah, we can't hear you.
You can't hear me.
No, we can't hear Joseph Curtin.
Oh, Curtin, okay.
Let's see if he can. No, we still can't hear you.
And he's not muted, so.
You know what, Joseph? We're going to go to Joseph Stradivari first while you try to figure out your computer, okay? Okay, Joseph Stradivari. Go ahead.
I'm trying to come up with some explanation to the odd case of violin 1, which is very close to 5 and 11 and is disliked by virtually everyone. I wonder if you considered the possibility that a violin can be rejected by a player based on one single note, which is very defective. For example, on many violins, the note B around 490 hertz can have very low emission, and also many times the highest notes on the violin, sometimes the D or E, have very weak fundamentals. So just one place on a violin can be, one bad note on the violin can be a reason of rejection.
I agree with you, but it's not because of this. For one, it's a question of like tone quality, or maybe Giorgio and Unai would like to describe the quality of this violin compared to.
So
they can be recognized, not just because of one note.
Would it be not worthwhile asking the players who do your studies next time to ask that question, is there a particular note that annoys them? Because that is very easy to hear on many violins, both as a player and as a listener.
Okay.
Many times, listeners don't evaluate violins based on averages, but on the merits of the weaknesses. Something that really stands out from a violin many times, just one note can be the reason of rejection.
Yeah,
but you cannot play the Lalo Symphony Espagnole if the high E is very weak, because it's very exposed. So that's an example that one note can be the reason for rejection.
Yeah. I agree, but in this case, in this particular case, it's not the reason. It's a whole tone color of the instrument that was disliked.
Yes, maybe. May I ask a technical question? Could you tell me something about the density of the spruce that you have used for this study? The density and the weight of the bellies for the violins of thin, medium, or thick. Do you have those numbers at hand?
At hand, yes. Or maybe, do you have them on top of your mind, Unai?
Well, I don't know. I mean, it's very important for a spruce whether the density is 0.35.
Oh, Anders just typed it into the chat. 0.367 to 0.381 for the tops.
Okay. Thank you.
All right.
Yes. Thank you very much.
Okay, thank you, Joseph. Let's go to Joseph Curtin. I think you've fixed your microphone.
Okay, can you hear me?
Yep.
Thanks for the excellent talk and huge amount of work. A couple of questions. I had to come in late, so I missed a bit what was the microphone distance for the radiation measurements?
So the radiation measurement, so the
25 centimeters, 25 centimeters, more or less.
Okay.
So your usual standard.
Yes.
Okay, and was that in a chamber or in a room?
No, in a quite asymmetrical room with some absorbent panels. We try to do more or less.
Okay, so well, one thing that's encouraging then is that even though the microphone's so close, you say it corresponds with listeners. That's listeners in a hall.
Yeah.
So I don't think we're so worried as Colin was saying about the interference of the room acoustics, at least on average. But my guess about the variation from player to player, at least at higher frequencies, would be the variation in position of the violin when they're playing. Because I know when I try and do recordings, that can really mess things up. So it seems to me the lower frequencies would only change with relatively big positions in the hall, and it sounds like that's what Anders is saying, but it seems to be the high frequencies could usually change by quite a bit just by the angle of the violin in relation to the microphones from the player.
Yeah, but we get 20, 30, 40 dBs even at low frequency.
That is very puzzling.
The
Okay.
second, third octave band is, so it's like, yeah.
So that sounds like an important next thing to look at, to try and narrow that down. The other thing I maybe missed was the loudness model. It seems to give loudness at different frequencies, but I don't understand that concept. Isn't loudness a sort of a global number for a total sound, not for individual frequency bands?
No, I mean, there are different steps. So first you compute the specific, what is called the specific loudness, which is for a given frequency. And then you can integrate these to give the total loudness. But we definitely didn't want to integrate it because we wanted to keep this frequency dependency.
And there were 371 frequency bins. It's not a continuum.
Okay, I understand. So the idea that if you took a single band, the instruments would sort themselves by overall loudness. Is that correct?
No, can you repeat?
Okay, so if you took if you did the loudness compensation model and then you did a single band for your whole frequency range for each violin, would that give the perceived loudness of the instrument relative to the others? I mean, is that the idea of this loudness?
Yeah, the answer is yes. That's what specific loudness means. Yes, yes.
Okay, and did it correlate with listener perceptions of loudness?
We don't have enough. No, we didn't look at this in particular.
Or projection, for that matter.
Yeah, we only looked at basically the
correlation with the.
We could compute an overall loudness for each violin and see whether this go with the loudness valorization.
That would be interesting. And also, if you took the overall loudness, would it vary how much from player to player? Presumably less than the individual bands, would you say?
We didn't compute the loudness per player. Okay. Because basically we said, okay, we have 23 players. We can see that there are huge differences between the 23 players. So we decided that we first average over the players, and then we use this as an input for the loudness model. So what we use for the loudness model is not a wave file, because normally what you do is you put a wave file and it calculates the loudness. Here we actually, but the first step in the loudness model is from the wave file, he calculates a power spectral density. So what we do here is we average over the players and we use this as the input, as a power spectral density, as the input for the loudness model. So basically the loudness that we compute is an average loudness over all the players per frequency.
I see. Okay, thank you. Thank you.
All right. Thank you, Joseph. I don't see any other hands raised, so I think I'll go next. One brief comment. It seems like one of the fundamental difficulties is evaluating a multi-variable thing. Because when people evaluate instruments, it's not just a single factor, but multiple factors. It's not just a simple weighting of those things. So that's just a comment, because I think that's one of the big challenges that you face. But the other thing, observation, is what John Fable had asked, which is, what's the next step? It seems to me the most interesting thing that you presented is some of the discrepancies between the listeners and the players' perceptions. There were, I think, one area you pointed out there was high correlation, but in many other areas there was not. So obviously there's additional information that the player has that's not getting to the listener, and that's affecting the player's evaluations of the instruments. And to me, that seems to be the most interesting area for research.
Could I just
Yes. Well, first, Claudia, do you have a response, or you want to let Colin talk?
No. I mean, that was basically the last point of the conclusion.
Yeah.
Discrepancy between 1, 5, and 11, for example. That in the measurement it's the same, but it's not perceived like this. So that means that there is something that they have access to, which is not in the measurements we have. But then between the players, the thing is, with this data set, I feel like we need more about the players. And we have another bit of the data set that we haven't presented at all here, is because basically what happened is, like, then the violins, after the Bilbao tests, the violins were taken to Oberlin, and then we did a second series of playing tests and listening tests. And so maybe we should look at the data there as well. Because from the categorization task, I feel like we have already done a lot on analysis, and I'm a bit worried that the quality of the data is not as good as we could have hoped for. And I think it was too difficult, the task. And to be honest, I have doubts that if we have asked the same players to come back the next day, that they would have done the same groupings. It was very difficult. Apparently they got lost. Not necessarily all of them, but to actually, I feel like this categorization works better for things which are a bit more different. So I use this because I talked to a psychologist. He said it's a great way of getting data, and I really can see the point. In cognitive psychology, it's been very useful. But she's always been using it for like more different things, well, for environmental sounds, and they want to understand what is really important for people, and how they would classify the different sounds from nature and from the cities. But here, in the end, there is not something which looks more like sounds more like a violin than another violin. So it's very certain, and so I think that task with certain violins for players, especially if they are not used to that, if they can be good players but not used to pay attention, then they probably have lost track. And so I think the data we have in terms of their preference is still meaningful, and it correlates quite well with what we have seen after that. But for the categorization task, I'm a bit worried that the data are not that as good as we had hoped it would be. And so maybe we shouldn't try to push too much effort in this direction, because if we have to do it, we should redo it in a different way. So what we did at Oberlin, we only had the 6 instruments and not the 13 instruments.
Were these Were these the instruments?
We
This
only
is from-
had the belly instruments. We only so when we took them to Oberlin, only the 6 which were made belly school were
I think those are the 6 instruments in my background shot, right?
Oh.
Yes,
I mean,
yes,
I didn't actually. I was looking for a background picture, and this was like literally 3 minutes before I got on, and so this is the first one I found. And then that after I got it, I realized, maybe these are the actual instruments.
Yes, indeed, indeed. And so in that case, I think they were. So we should look at this data as well in terms of what players said, and the people who took part were able to identify some of them, and so I think that's a better data set.
Okay.
But it's just like we wanted to kind of like finish analyzing the Bilbao data set before going to the Oberlin, because it's just so crazy to have all these things.
Right.
We, these sort of things that, we could correlate this with this, we could look at this, and it just keep growing and growing, and then we could do this and we could do that, and then just like hard to keep track as well. And sometimes we do, and then we don't get anything, and then we forget that we have done it. We have to look at our notes. Yes, we had already checked this, and yes, it didn't work. And yeah.
Okay, let's have one final question or comment from Colin.
Yes, I mean, going back to Fan's comment about the difference between the player and the listener, which is all important. I mean, violins can sound incredibly different under the ear, judging the quality and the distance. And one of the reasons for that is, of course, that the point is that the sound that one's hearing, when you're close to the instrument itself, you are hearing something intrinsic to the violin itself. But as soon as you get away from the violin, well away from the violin, in a room, you're picking up all the resonance of the room as well. So you tap an instrument and you'll get the ringing of the room. We all know rooms have a decay time of a couple of seconds and things like that. And that really dominates the way the actual physical sound is actually measured. But the interesting thing is there's a fundamental thing about is how do we hear the quality? How long does it take for us to hear the quality of an instrument? We can detect where something is within about 35 milliseconds. That's the response that the brain sort of responds to signals coming into the air. Really, if you can actually start to hear the quality of an instrument in terms of a short time like that, perhaps it is the radiation that's coming straight towards you rather than the radiation that's running around the room, that one can start to judge the ability to recognize what sort of sound it is. After all, it goes back to these primeval sort of reflexes. You not only want to know if there's a sound, you don't mind the rustling of the grass, but if it's some animal coming up that's making some sort of noises, you want to know that pretty quickly. There's a fundamental question which I would like to know the answer to. And I mean, I think the psychoacoustics people can probably help us here, is how long does it take to tell what an instrument is actually playing? We all know that the initial transient's important. The initial transient's important, that's very short sounds, and it takes us back again to this business of transients being incredibly important.
Oh, it looks like we've
I feel like
all these people have now.
How long does it take to hear
questions?
the quality of a violin? I don't know if we actually hear the quality of a violin. We have done tests, unfortunately, you were not here in Bilbao this year, but we have done tests where we just can't hear anything. Just like we couldn't, as you had a player playing 2 violins in a row, we had to say whether it was the same violin or 2 different violins. We were not able to do it. So what is the quality of a violin? We don't know.
Well, it's interesting. If you tap a violin you can tell quite a lot of information from the sound of the tap.
Yeah. Well, let's
yes,
go to
the
Jim.
sound of the tap, yes, but how does it correlate to what you hear when you hear the instrument played by a player? It's a different matter.
Well, I mean, we go to a lot of extent of taking things like the acoustic spectrum in detail and assuming that it actually has got something to do with the sound. And somehow, I mean, those of us that have a rational view of sound and things like that, rather than think it's the love of the instrument and all the rest of it, feel that somewhere in that mess of spectrum, there's something that's telling us something about quality. We still don't really know.
I mean, obviously, if we were able to have a 0.7 correlation between the listening perceptual data and the radiation measurements, it means that there is something. But it's only 0.7, and with the test we did in Bilbao, we realized that the influence of the player is so huge that it can really mess things up.
It's not the same input for all the violins, and even the violinists finally could change their way of playing.
There's no doubt at all that the player can influence the sound of the instrument by what goes into the instrument, as Jim has got some lovely demonstrations. I mean, it's the player, most of the sound and the quality we hear of a violin is that's produced by the violinist bowing the strings. And then there's a filtering action of the violin itself, which is what we're worrying about, and that's what the maker can do something about. But that doesn't change the sound very much from sounding almost like a violin from the strings alone. And it's the ability of the player to make a nice sound on the strings that's all important in the sound that we get excited about when we listen to a great player.
Yeah, but you say so, but at the same time, having a player playing different violins, we were not able to say whether he was playing the same violin or different one. So
you could differentiate the player, but not the violin.
But you're listening. But I'm sorry, you're listening to it in an acoustic, and it's dominated by the acoustic, possibly.
Yeah,
Joseph's comment. Let someone else speak.
But we are always evaluating violins in an acoustics, So,
All right, let's go to Jim.
This is just a quick comment on what Colin said at the beginning of their. He was talking about the difference between the sound under the ear and the sound in the hall, in terms of the reverberant sound in the hall. But of course, the player is so close to the instrument that the player is hearing the near field of the instrument. There's an important technical distinction.
Absolutely.
The player is hearing non-radiating modes. Only the strongly radiating ones make a difference to the sound in the hall. And that's a second thing which is also important. That the player hears all kinds of stuff which simply does not radiate. All those, the player will hear CBR, which doesn't radiate sound at all.
All right,
that's all.
Joseph.
Well, firstly, is that true, Jim? Do we know that? I mean, if you plug your ears and play the violin, you can hear B0, these long rings and things, but when you take your earplugs out. So I don't agree or disagree. I'm curious, has anyone studied that?
This meeting is being recorded.
I think the comment I intended to make is uncontroversial. That if you play with a microphone, if you record with a microphone right on the surface of the violin, every mode will contribute. You have to move away further away than you do in your measurements before you really, for the lower frequencies, before you really get dominated by the things that we tend to calculate in the sound radiation models. The player's ear is somewhere in between. I mean, one ear of the player is right on the surface of the plate, much closer than you would ever do your microphone measurements. So of course they hear something different. Whether it matters, I don't know, but it's as an acoustical statement, I think it's uncontroversial.
Yeah, Joseph,
Okay.
can I give you a slightly different example? Because I remember walking into a room of a guitar maker. This was at a guitar making convention, and everybody was oohing, eyeing over the incredible bass sound of a bass acoustic guitar. And I had no idea why they were so enthusiastic about this bass guitar, because I couldn't hear any bass when I entered the room. But then when I went up to about where everybody else was standing, which was about 6 feet away from the bass guitar, there was a tremendous amount of bass there. So there was a psychoacoustic, sensitivity issue, which, that was in play. But the basic message there is that, yeah, there's a difference between what you hear very close versus very far. In this particular case, it has to do with psychoacoustics, but I think Jim's case, he's talking about, non-radiating versus radiating modes.
Okay, I accept that. That's fine. But I did a reaction to what Colin said about when we're in the near field, we're not really hearing the room acoustics the way the listeners are. But is that true? If we play a violin in an anechoic chamber, it sounds completely different than if we play it in a loud room.
Sounds horrible.
And we're very affected by the acoustics as players. That's why players complain about different rooms. It's just a different process. I think in a small room, isn't it the case that the reflections are integrated, so it sounds like it's coming out of the sound. So we hear the sound is louder, whereas in a hall, you hear it as an echo. And David Greisinger, I think, had an interesting point. Maybe we can ask him that. I think it was, at least for singers, they suppress the sound that they make, and he presumes that's true for violinists, which would actually go a long way to explaining why this difference between what players judge and what listeners hear, or perhaps it could. Anyway, that's everything I have to say.
All right. John, you're next.
I just wanted to mention this whole notion of psychoacoustics and how we hear and how different people hear differently. I put a note in the comments about a book that my neurobiologist cousin just published called Of Sound Mind. She got written up a few years ago in Strad because she really finally put the biological basis beneath why when we study music, why that has cognitive benefit, right? Of course, that was, and that's just one of hundreds of papers that she's literally published on this. But she and I have had all sorts of conversations around this and this very topic. And the book Of Sound Mind is sort of a lay science book, but this whole topic is very close to her heart. Claudia, I've been meaning to put you and Nina together, so I will finally do that. She's at Northwestern, so anyhow, so I put the link, not the link, but I put the title and Nina's name in the comments.
All right, Anders.
Yeah, I was thinking about the situation an orchestra musician has. You sit in the orchestra, there's a lot of sound, and in some situation, I think they don't hear themselves so well. And I did an experiment, and I've also heard Claudia talk about this, that some musicians are able to intonate from the vibration information they get in their hands from the neck. I put the air mufflers, and under there I had the earplugs, and I could still tune my instrument and play, no problem. And I think there's some part of the sound comes through the chin, and there's some bone conduction going on, which also probably on a low level colors the perception. And I think I've tried to go out on the stage on the Warner Concert Hall in Oberlin and play there, and it's a very different experience from playing at home, where you have the reverberation much closer to you. At the stage there at the concert hall, I could hear almost nothing, only the instrument, and it's a very different experience. And yeah, that's all I wanted to say. You know, I've grown up with my father is a Hardanger fiddle player. He's a professional player. He was very good early, and during his 20s, he was playing every day at home. And one of the things he used to do was to sit and listen to the sound coming back from the room. It's quite clear that there's not many musicians that prefer to play in a echo-free room. So reverberation is quite clearly one important part in the experience of music. It's quite boring without it, and it's even difficult to speak and to give speeches if the reverberation is too short. So reverb is a good thing, and it's information from the source, not from the room. It's from the source. It's only distributed back to you from the room.
Claudia, do you have any last words before we end?
I'm tired.
Okay, so then let's give a great round of applause to Claudia and her whole group and her team for this, all the work
It's
you've
not
done.
my team. It's don't have any. No, yeah, it's not a leader. There is no leader. It's all a very collaborative work.
Yes, yeah, it's a wonderful group of people. So I'm going to keep this open because I know a few of you might